Hey, what's up, everybody? It's Miss Brothers. I just want to walk you through this test. Now, the test that you see here, this is the B version of the test. The good news is all three versions were the same. They were just in different orders. So even if you took the A or the C version of this test, just know that the questions were the same. So I'm going to walk you through that. All right, so if we are looking through, oops, sorry about that. I'm going to do that a lot during this because I'm still, getting familiar with all this. So the way this works, you guys, I'm simply going to walk through the questions, show you the correct answers, and then kind of talk a little bit about how you can recognize what the question is asking. Because what I find with a lot of my students is that you just struggle to understand what you're being asked when you're taking a test. Okay, so here's our first question. It says the measure of the amount of kinetic energy or energy of motion in matter. Now these two questions, if we're looking at them, these two questions are really similar. The answer is either heat or temperature. So that's going to be either this question right here or this question right here. They're essentially asking for the same thing. So this one is asking for the measure of the amount of kinetic energy. Now, one of the things you have to remember, if you see the word measure, that is an indication that you are dealing with temperature. Because think about it, you guys. If you're taking the temperature of something, you're putting a thermometer in it, you're taking its temperature. That's how we measure it. Now, if we are looking at this next question right here, this question, it's asking for a process. That's the big difference. Now, on the very first day when we were defining heat versus temperature when we did this unit, we defined heat as the process where energy moves from systems of high energy to systems of low energy. So that's one of those things where you just have to remember that heat is a process and temperature is a measurement, and we talked about that the very first day that we did this unit. All right, next question. The picture below shows which type of energy transfer. Well, again, you guys, the three types of energy transfer are convection, conduction, and radiation. Convection is when we are dealing with heated fluids that carry energy with them. Radiation, we are dealing with electromagnetic waves that carry energy. And conduction is where we have direct contact. And that's what you see with these particles here. So essentially what you see is you have one particle that has energy, and it, by touching these other particles, through those intermolecular forces, it spreads its energy. And then as these other particles are touching other particles, they are spreading their energy. So conduction is direct contact. Next question. Match the correct type of heat transfer. So again, we're on this question right here. Match the correct type of heat transfer with the description. A lava lamp, that's the one we're on right now, uses this type of heat transfer. Well, you have to think about what's in a lava lamp. A lava lamp is different types of fluids. So as a result of that, because we're dealing with fluids, we are dealing with convection. Heat transfer in solids. Well, again, you guys remember that when we are dealing with solids, solids are tightly packed together. And that's not a very good solid. I'll do a little bit better with my solid here. There we go. So solids are particles that are tightly packed together, and if they're tightly packed together, they're in direct contact with each other, and if they are in direct contact with each other, then we are dealing with conduction. Next up, this one right here, heat transfer that happens through the flow of heated fluids. Well, there's heated fluids again, just like we had up in this one. So as a result, this one is going to be convection again. So this next question, the ice block demonstration showed this type of energy transfer. Well, what we had when we did the ice block demonstration is we had a block, and then we had an ice cube on top of it, and then this ice cube right here started to melt, okay? So you have the ice cube, it is in direct contact with the surface, so energy is being transferred from the surface up into the ice cube. And again, you guys, if we are dealing with direct contact of particles, then again, we are dealing with the types of conduction. Now, one of the things that you'll do as you go through this remediation, as you prepare for the retake, is that you will spend a lot of time with vocabulary, and radiation, conduction, and convection are parts of that vocabulary. All right, last one right here. This type of heat transfer does not require matter in order to transfer energy. And again, we talked about the fact that up here, that when we are looking at radiation, which is heat transfer through electromagnetic waves, it doesn't require any sort of matter in order to conduct that energy. Both conduction and convection do. Convection requires fluids, and conduction requires direct contact between two different sets of particles. So as a result of that, your best choice of answer there is going to be radiation. All right, next question. So this is a vocabulary question right here. A process where energy is gained or absorbed. Well, your two prefixes are either going to be endo or exo. And I always remember it by using exo because I think this is the easier one to use. The prefix of exo is ex, which is the same prefix if you have the word exit. So exit means to leave or you're released. So that would be, if this would have said released, then you would have said exo. But because we have things that are gained or absorbed, that's endo. And that's, again, that definition. Part of the challenge of this unit is that you have to have a really good, strong grip on the vocabulary. And like I said, that's one of the things that you'll be doing to prepare for the retake. So again, you should have chosen endothermic because endothermic means something is gaining or absorbing energy. All right, next. Heat transferred by the collision of particles. Again, there it is. Collision of particles, and by when particles collide, we are dealing with direct contact. And if it's direct contact, it means that we're transferring energy through conduction. Next question. Energy is transferred as less dense fluids, look, there's that word fluid again, rises and carries energy upwards. And again, you guys, if we're dealing with fluids, we are talking about convection. Next question, the process where energy is released. Okay, again, if it's released means energy is exiting a system. So again, you guys, if it's exiting a system, boop, boop, there's that prefix, that's going to be exothermic. Next, measures the kinetic energy or motion of particles. And again, this is another vocabulary word, so we're looking for something that is a measurement. None of these other ones, conduction, convection, endothermic, or exothermic, none of those are actually measurements. These are all processes. The only measurement in the group is temperature, so you should have chosen temperature as your answer. And again, you guys, just by definition, temperature is us measuring the motion of the particles in the substance. All right, moving on to our next learning target. This is 1.2D, our phase change in energy learning targets. All right, so if we are looking at this diagram, the red arrows, in this case they're blue because I'm making them blue. The red arrows, you guys, represent energy. And what we have in here is we have energy going into a system. And if energy is going into a system instead of exiting the system, we know that this has to be endothermic because energy goes in. This is another way of saying energy is absorbed. If energy is absorbed by a system, it means energy is going into the system. All right, question. I'm on this question right here. Which of the following is not a unit used in the calculation of thermal energy? The tricky part of this question is that you have to know the formula to calculate thermal energy. So this is the formula that we spent almost that entire last week working with, and that formula is Q equals the mass of a substance times its change in temperature times its specific heat. So again, you guys, one of the things that you'll be practicing as you prep for this retake is this idea that if we're going to calculate thermal energy, we're going to use that formula. So if we are looking at this, one of the things you have to understand is the difference between symbols versus units. That's the first thing. So symbols are abbreviations. We use in an equation. So if this is our equation right here, and it is, that's our equation for thermal energy, each one of the things in here is a symbol. Q is a symbol, and so we'll go over here and just kind of make a little room here. So Q is our symbol for energy. Okay, M is our symbol for mass. Delta T is our symbol for the change in temperature. And Cp is our symbol for specific heat. Okay. Now a unit, on the other hand, so I'm going to go ahead and draw a little line here, so I'm making this lovely T chart. A unit, on the other hand, is a designation for measuring. For instance, if you're baking a cake and it calls for a cup of flour, the cup of flour, that cup is the unit. How much flour? It's a cup of flour. So units are what we use when we are actually measuring something. So these are a designation for measuring. Now, for Q, if we are going to measure energy, we use the symbol joule, otherwise known as a J. For mass, the unit for mass is grams. If we're doing a change in temperature and we measure it, we're going to use degrees Celsius in science. And if we're going to use specific heat is this big funky unit, joules over grams, degrees Celsius. So let's go back to this question. This question is, which of the following is not a unit used in the calculation of thermal energy? Okay? These are all the units that we use in the calculation of thermal energy right here. J for joule, G for gram, degrees Celsius, and joules over grams degrees Celsius. So the only one that stands out that's not a part of that formula or that part of that calculation at all is L. And this is actually the unit for liters. So this is one of those things right here that kind of trips students up. And part of it is that you have to know the difference between a symbol and a unit. And again, you guys, units are what we're using in order to designate a measurement. And a symbol is what ends up being in an equation. If we had to write out, think of it this way, you guys. If we had to write out all of these words instead of using these symbols right here, this equation would be 4 times longer. Okay, now I know it may seem weird that you use Q to represent energy, but you have to understand that a lot of these symbols and abbreviations were created when people were still using the Latin language and that alphabet. So some of these things get carried over. So don't get too caught up in that. Just know that symbols are abbreviations for when we're making a whole formula, and units are what we use when we're designating measurements. Okay, let's move on to the next. I know there was a lot in that one. All right, so here they are again. Symbols. What is the symbol for thermal energy? Thermal energy right here. So again, if we go back to our little T chart that we made right here, we see that our symbol for thermal energy is Q, and that's just something that you really just kind of have to learn and memorize and practice with. So again, that's something that you'll be doing. All right, so this diagram shows which energy flow process. Well, these arrows again are representative of energy, and so here we have our system. And this time we see the energy exiting. So energy is exiting. All right, oops, I'm gonna actually make that look like the word exiting. That's the spirit. So energy is exiting. There's that prefix exiting. So we are looking for that prefix right here, exothermic. Boop. All right. Next question. Which of the following is true about specific heat of a substance? Well, again, you guys, one of the things you have to know is you have to know the definition for specific heat. Specific heat is, by definition, the amount of energy it takes to raise the temperature of a substance (1°C). So that's the actual textbook definition. One of the things you have to understand, if you really want to truly understand specific heat, it's this. How fast does something heat up? And specific heat is kind of, we'll call it an indirect relationship. What it comes down to is this. The lower the specific heat, the easier it heats up. Those are some things you have to remember about specific heat. So with that said, what that means is that the lower the specific heat number, so we're looking for which of these statements that are true. This one says low specific heat equals substance heats up slowly. Well, that's not true because we just said right here that the lower the specific heat, the easier it heats up. So that means it should heat up really quickly. So it's not that one. This one, low specific heat equals substance heats up quickly. That's pretty much what we just said. So that should be the one we picked. This one down here that says high specific heat means substance heats up quickly. Nope, that's not what we just said at all. It's this idea right here. The lower the specific heat, the easier something is to heat. All right, this question is tricky, and this is one of those questions that's dependent on you understanding this equation. So Q equals, again, the mass times the change in temperature times the specific heat. So let's go ahead and read through this. It says an aluminum baking sheet with an unknown mass warms. Now that's a huge clue right there. Because what that means is that your answer, if you see warm, it means Q is going to be a positive number. Because warms means our system is gaining energy. Okay? Now, so with that said, I don't have to do anything else. If I see warm and I look at this is a negative number and this is a negative number, then I know that those two are automatically crossed out. I'm like, I don't even have to pay any attention to those. And because, you guys, this is the other clue. I'm trying to find Q. And according to our little T-chart that we did up here, if I'm trying to find Q, it means that the units I'm going to have when I'm done doing all my calculations, the unit of Q is joules or J. So that's the other clue of this. I don't know, as long as I know that Q is positive, it means this number's that means warming. And as long as I understand that the final unit has to be joules, then that's as far as I have to go. This one, the final unit is joules over grams degrees Celsius. That's actually a unit for specific heat. So that can't possibly be right either. So I can just cross that one out, meaning that the only one that's left that makes any sense whatsoever is that one. So you don't have to do a bit of math to do this one. You just have to know that when Q is, when we see the word warms, it means Q is positive. Now, if this word had been cools instead, then we'd be looking for a negative Q number. Because again, Q is all about how much energy we're either gaining or losing from a system. All right, next one. It says, during a summer visit to the beach, you'll notice that the sand burns your feet, but the wooden boardwalk does not. So the sand burns my feet, but the wood doesn't. So what we're trying to figure out is what must be true about the sand and the wood, and this is specifically a specific heat question. Okay? So what we're talking about here is which one heats up faster. So this is about what heats faster. The sand has a higher specific heat than the wood. That's not true, because the sand is really hot and the wood isn't. That means that the sand has a lower specific heat. So we know that question can't be true. This one says the sand has a lower specific heat than the wood. This is your correct answer, because if the sand is burning us but the wood isn't, that means that the wood is much harder to heat up and requires a lot more energy. So that means that the sand has a lower specific heat. And then this last one says the specific heat capacity of the sand and the wood are equal. That's not true, because if that were the case, then our feet would be experiencing the same thing on both of those surfaces. All right, next question. The amount of thermal energy change in a substance depends on what? Well, again, you guys, this question is asking about this equation right here. So if we look at this equation, Q, which is another way of saying energy, so energy equals the mass of a substance. So look, the mass of a substance, that checks. The change in temperature of a subject, oh look, there it is right there, and the specific heat. It's the worst parenthesis ever. Oh look, there it is. So the amount of thermal energy change, which is what Q stands for, depends on all three of these things, because all three of these things are in the equation. The change in temperature, the mass, and the specific heat. So you should have chosen all of these. One of the things you want to do, this is a test-taking clue, is that if you're going to take a test and it's multiple choice, get used to reading every single answer. Because you might say, oh yeah, it's change in temperature, boop, I'm only going to pick that one. But if you're being asked to choose the best answer to this question is right here. It is all of these. So make sure that when you have any multiple choice test, that you always read every answer no matter what. There's no hurry, so you might as well do that. All right. Of the substances listed in the table below, which would take the longest to heat from 20 degrees Celsius to 100 degrees Celsius? Assume identical heat sources. All right, so this is, again, we are given the substance right here, and in this column we are given the specific heat. Now, the reason we know this is specific heat is because of the unit. This unit right here, joules divided by grams degrees Celsius, is the unit for specific heat. And what did we say earlier about specific heat? The lower the specific heat, the easier it is to heat up. So the question again, which would take the longest to heat up? It's whatever one has the highest specific heat, otherwise known as CP. And if I look right here, aluminum has a specific heat of 0.897, which is larger than the other ones, or higher than the other ones, so you should have chosen aluminum. All right. Next question. Melting and boiling are examples of which process? You should have chosen endothermic, and the reason it's endothermic is this. If I have, here's my stove, here's the burner on my stove, and I put a pan of water, boop, sorry for my terrible drawings, on the stove. If I want this water to boil, it means I have to put energy into this pan in order to get this water to boil. Okay? So melting and boiling, if it's an ice cube sitting in here, it's the same thing. If I want to get this ice cube to melt, it means I have to put energy into it. As a result of that, this system is endothermic. Next question. Liquid particles are present during which of the following? And it should have been all three, because remember that time that we did that phase change diagram that looks like this, and we said that our phase changes are happening right here, and I'm just going to abbreviate that PC. And if I've got a liquid at this point, because this is essentially melting and freezing right here, and this is essentially vaporization or boiling and condensation right here, This means that I'm going to have liquid particles at every single place here. As this melts, I'm going to have a few liquid particles here. Definitely going to have some liquid particles here. As this liquid heats up and starts to vaporize, I'm going to have some liquid particles here. So you're going to have liquid particles at all three of these different phase changes. You should have picked all three. All right, next question. Which of the following is an example of an exothermic process? Well, let's take a look at our water again. So this time, you guys, we're going to take a thing of water. Boop. And there's my water, liquid water. And I want it to start freezing. So I take this and I put it in a great big freezer. Look, this is a freezer. And I want this liquid water to become ice. If I want this liquid water, boop, to become ice, that means energy has to leave this water. If the energy doesn't leave the liquid water, it will never freeze. So this freezer is going to help that. So you have a freezer that has significantly less energy than this water. The energy starts to move out of the water, and after a while, this is eventually going to freeze to ice. So because we have energy exiting the system, freezing is exothermic. All right, next part. All right, so we are looking at this graph right here. So the question is, based on this graph, areas B and D, so here's area B right here and D right here, what are they showing? They're showing phase changes. As long as we see a plateau, boop, then we are seeing phase changes. Next question. Based on the graph, when a substance is going through the process of melting, the temperature is doing what? Well, we have melting that takes place right here. I'm going to go ahead and find a blue here so I can show you melting and freezing. Here we go. So if we are melting right along this line right here, we're not showing a temperature change. If it's 5 degrees, okay, and this is that line right there. As long as we continue to add thermal energy and our phase is changing, we are not seeing any change in temperature. So our temperature is staying the same. All right, next question. All right, let's take a second, you guys, and let's go ahead and color this up. So I'm going to go ahead and make substance A pink. So here's substance A. It's pink. I'm going to make substance B this fun green color. So this is substance B. Okay. And then we're going to make substance C this fun blue color right here. There's substance C. Some might say that's purple. I really don't know. So we have these three different substances. All right. So the first question is, and we're going to be right here, so you know where we are. Use the diagram below to answer this question. At 150 degrees, what is the state of matter of substance C? So again, substance C is this kind of dark purple line. So the first thing we're going to do is we're going to find 150 degrees. So here's 100 degrees right here. Here's 200 degrees right here. We'll go ahead and say this is somewhere in the 150 degree range. We're going to draw a line across, and here we are. And then remember, you guys, if this is melting and freezing right here, and this is vaporization right here, then we are looking at the gas phase up here, and we are looking at the solid phase down here. So this would be a liquid. And so that's what we would choose for this answer, liquid. All right, which substance? Oh, we're going to have to do this again. So there's C. Oops. All right, there's substance C. There's substance A. There's substance B. And substance A. All right. So, again, when we're looking at this, it says which substance has the highest specific heat. Well, we're going to use our kind of line to gain. Our goal line is 400 degrees, which is this line at the very top. Now down here at the bottom, what we see is that our x-axis is labeled with time. And what that means is that time is increasing as we are moving this direction on the graph. So my question to you is, which one of these substances, A, B, or C, reaches 400 degrees the fastest? Well, it looks to me like substance A reached it in about 180 seconds. Okay. Substance B reached it in about, I don't know, we'll say 310 seconds. And look right here, substance C hasn't even gotten there yet. So in this time frame right here, substance C still hasn't reached 400 degrees. So which one has the highest specific heat? It's the one that takes the longest. Oops. So whatever substance takes the longest to get to 400 degrees, that's the one with the highest specific heat. It only took substance A 180, so we know that it's not substance A. It took substance B 310, so we know it's not substance B. Substance C never even got to 400 degrees. So as a result of that, we know that whatever substance C is, it is very resistant to being heated. So we can say that it has the highest specific heat. All right, next question. And again, let's go ahead and what did I do for those? Pink, green, and purple. All right. Pink, green. Oops, I did that wrong. Oop. Green. Purple. I guess it was kind of more of a blue than a purple. All right, so there they are again, A, B, and C. This question, which substance has the lowest specific heat? This time, you guys, if it's the lowest specific heat, it means this is the one that heats the fastest. And what we already figured out, based on the fact that substance A only took about 180 seconds, it's A has the lowest specific heat. All right, this next question, the melting temperature of B. So again, substance B is this substance right here. Oops. Sorry, I keep doing that wrong. Substance B, right there. The question is, what is the melting temperature for substance B? Well, again, substance B plateaus right here along this line that you're seeing me draw. So at the very point along here, it looks like here's 0 degrees right here. This starts going through its phase change right about here, which is somewhere below 0. So as long as we pick something, a temperature that's below 0, the only one that's actually below 0 is -20, so it's got to be that one. All right, and that is the end of this test. I know this took longer than maybe you wanted to sit through, but you have a much better idea of what I was looking for in these questions. So you, like I said, this is part 1 of your remediation. The next part, you're going to do some vocab work, and I think you should be solid enough to really improve your score for the retake. Thanks, you guys.